last week's resource, week 4 resource, I have provided in the folder Rectifier-01 this rectifier schematic. So here I have included some non-idealities. I have included line inductance 0.01 microhenry, very small value, lumped line resistance 0.1 ohms, and a non-ideality track inductance here of around 1 microhenry, all small values. In fact, if this inductance is made very large, then it can become an LC filter. But normally you don't use an LC filter in practice because the L is very costly and very bulky and it has to carry the entire load current. So normally L is not used, but this is a distributed inductance shown lumped here for us to study the wave shapes. So now let us simulate the circuit. As the mains, I am giving input voltage 325 sine omega t. So this is a sine voltage of peak amplitude 325. And let us see what is the wave. This is a normal circuit. We are interested to see the first cycle inrush current. So let us observe that. So let us go to the terminal, open the terminal, and let me make the netlist and run the simulation in ngSpice. So for that, what I will do, I will type, I have made a small update, just a help file run sim, so that it will make the netlist from the schematic, and from the netlist it will call the CAR file and run the simulation within the ngSpice environment all at one go, and it will also plot directly. I will show you how to do that shortly, but anyway, let me use this help file. Rectifier, just type in the rectifier, it will automatically take the schematic extension. So run that. So it will run and you will see that I have got the plot out. Let me expand that. Observe this. What is this red waveform? That is VAB. If you go to the schematic, VAB is the input grid. Current through LS will be the input current. Okay, we are monitoring current through LS, we are monitoring the input waveform, and we shall also monitor the output voltage V0. So when you go back to the waveform, so you see this wave shape is V0, VAB is the red one, and the blue wave shape, what we are seeing is the current, input current. Because it's the input current, you see it positive, negative, positive, negative. Look at the first cycle. So it's around 100 units, 100 amps. First cycle is very large, and then immediately the steady state is reached. Okay. Now this is the benign case where the input voltage is going from 0, gradually rising from 0. Let us take the case when it is not benign, when the input voltage is starting at the peak value. When you switch on, the input voltage happens to be at this point. What happens under such conditions? Let us see. I will make one change in the schematic here. I will click on this and introduce an advance. I will give a lead of 5 milliseconds, which is 90 degrees. So it will become a cos wave. So I have changed that. Let me save this and redo the simulation. So go back to the file, command line, type in this. It will make the netlist, compile, run, and let us have a look at the wave shape. Look at this. You see that to fit into the same graph, everything has to be compressed. This is still the same 325, but look at the startup inrush current. It is hovering around 2.4 kilo amps. This is 2.4 kilo amps, the startup inrush, and then it reaches the steady state. Now this is a dangerous thing, and this is what will cause your components to blow and not reach the steady state at all by the time the first cycle is over. So you have to protect the circuit for this first cycle inrush surge current. So now what I will do, I will make one more change just to demonstrate to you one of the most simplest solutions to solve this problem. Introduce a resistor. This was the lumped resistor of all the distributed line impedances, but I will make use of this resistor itself and put in a resistance, let us say 1 ohm, just to see what happens. You can calculate precisely what is the value that you would need. And we still will keep with the non-benign condition, a cos wave, and see what is the effect by making just this change by including this, increasing this resistance as a protection component. So let us save this, go to the terminal, rerun the netlist and the simulation, and you see the waveforms. So observe here, first cycle, it is around 325 amps. So you know V in was 325 and we gave 1 ohm as the limiting resistor, and therefore around 325 amps will be the inrush current, and starts coming down and becomes stabilizes. So you observe that from 2.4 kilo amps it has reduced to 325, of course by putting different value of surge resistances, input resistances, you can improve the inrush current limiting. On the other hand, observe that the output wave shape also changes by, it is not, it would have dropped down because of the drop across the resistor. So these are some effects. I would suggest to you to play with these values, play with the values of these non-idealities to get more insight into the circuit, especially for the inrush surge current limiting action. Before we change the topic, I would like to tell you on the small help file that I made. Let me go to the bin file, bin directory. That is where I have kept this ls. So let me type in run sim. So this is the file that I have placed in the bin directory. You can do that likewise yourself and look at these command lines here. See, basically what I'm done is, instead of the system command which we did last time to generate the netlist using gnetlist, I have put it here as a system command in Octave and used it to execute automatically. Then after that, calling ngSpice and the CAR file, whatever you are typing in at this point as a variable. Okay. So this is a simple help file. You could use it or you can modify it as you please. Another small modification which I made is in the .cir file. So open .cir file. I have introduced a set of control statements here. Observe this. So between this .control and .end C, some control statements which will work within the ngSpice environment. So once it goes into the ngSpice environment, automatically this will get executed. It will set the background as white for the plots, foreground will be black. Then run the simulation once it enters the ngSpice environment, and plot VAB. VAB is nothing but this one, this voltage, input grid voltage, and ILS is the input input current, and V0 is the output voltage seen here. So these are the small modifications which I did so that it can help the simulation good. You can do the simulation a bit more faster during iterations especially.